Section 6.3, General Probability Rules. Rule 1, probability of any event has to be a value between 0 and 1. If the probability is 0, that means that event cannot happen. If the probability is 1, that means that event will happen. And then obviously anything on the scale between 0 and 1, closer it is to 0, the less likely it is to happen. Closer it is to 1, the more likely it is to happen. Probability of S, which is the probability that it is something in the sample space, is 1. Our addition rule, if A and B are disjoint events, then the probability of A or B happening is simply the probability of A happening plus the probability of B happening. Complement rule. For event A, the probability of A complement given by A raised to the what looks like to the C power is equal to 1 minus the probability of A happening. And the multiplication rule, if A and B are independent events, then the probability of A and B happening is the probability of A times the probability of B. The union of any collection of events is the event that at least one of the collection occurs. If events A, B, and C are disjoint events in the sense that no two have any outcomes in common, then the probability of A or B or C is the simple probability of A added to the probability of B plus the probability of Z. This rule extends to any number of disjoint events. So in this case, we had only 3 events, A, B, and C, but it doesn't matter how many events you have. If you're talking about events that are disjoint and you want to know the probability of one happening or the other happening or the next happening, simply add up the individual probabilities. So we can see here, the rectangle represents our entire sample space. Event A, event B, and event C, there is no overlap. That's what makes those disjoint events. If I want to know the probability then of A happening or B happening or C happening, we add up A plus B plus C. For any two events A and B, the probability of A or B is equal to the probability of A plus the probability of B minus the probability that A and B happen. So if we look down here, the second one here is just the same thing given in symbols. Union symbol is read as our OR statement here. So union is OR and intersection is AND. So when we're looking at this, the probability of A or B is the probability of A plus the probability of B minus the probability that they both happen. Our Venn diagram gives us a better description of what this is telling us is going on. So again, the rectangle here down at the bottom represents our entire sample space. We have event A and event B, and we see that we have an overlap. There are some things that happen in A and B. So when we go to find the probability of A or B, if I stop right here and I simply add the probability of A plus the probability of B, everything in this middle section right here is being double counted. Because I counted it when I counted A, I counted it again when I counted B. So what we need to do, because these are not disjoint events, I need to then turn around and subtract out the probability of A and B happening to ensure that I'm only counting those things one time. Also understand that if we're talking about disjoint events then, events that do not happen at the same time, then this is always going to be 0 if they're disjoint. Which is why for disjoint events, what's boxed in green here is how we find the probability of A or B if the events are disjoint. The intersection would be 0 because nothing happens in common. Looking at our first example here. Call a household prosperous if its net income exceeds $100,000. Call the household educated if the householder completed college. Select an American household at random and let A be the event that the selected household is prosperous, B be the event that it is educated. So let's write those down, make sure we know what we're doing here once we get our symbols. So A is going to represent a prosperous household. B is going to represent an educated household under the guidelines that we were given here. Prosperous household income is over 100,000. Educated if the householder has completed college. According to the current population survey, the probability of A is 0.138. So the probability that the house is prosperous is 0.138. Probability of B, probability that that household is educated, meaning that the head of household has completed college, is 0.261. And the probability that a household is both prosperous and educated is 0.082. So the probability of A intersect B is 0.082. We want to know what is the probability of A union B that the household selected is either prosperous or educated. So I want to find the probability of A or B, which we know is found by taking the probability of A plus the probability of B minus the probability of A intersect B, that they're both prosperous and educated. So to calculate this then, probability of A we're told was 0.138. Probability of B is 0.261. And the probability they both happen is 0.082. So we add those up, subtract the 0.082, and we get 0.317. So there's about a 31.7% chance that a randomly chosen household is either prosperous or educated. Problem 68. Stephanie is graduating from college. She has studied biology, chemistry, and computing, and hopes to work as a forensic scientist and apply her science background to crime investigation. Late one night, she thinks about some jobs she has applied for. Let A, B, and C be the events that Stephanie is offered a job by A, the Connecticut Office of Chief Medical Examiner, B, the New Jersey Division of Criminal Justice, or C, the Federal Disaster Mortuary Operations Response Team. Stephanie writes down her personal probabilities for being offered these jobs. Probability she is offered job A is 0.6, job B is 0.4, job C is 0.2, and then she has her personal probabilities for being offered any combination of two of the jobs or being offered all three. Notice her probability of being offered all three, she is calculated to be 0. So that is not going to happen according to her calculations. Letter A, make a Venn diagram of the events A, B, and C, as in figure 6.9 on page 439. Mark the probabilities of every intersection involving these events and their complements. Okay, so we have a rectangle here that is our entire sample space. We have event A that could happen. We have event B that could happen. And we have event C that could happen. So let's call this event A, event B, and event C. Let's look back at our probabilities here. We know the probability of A and B happening is 0.1. So let's fill that out first. So A and B is 0.1. Probability of all three happening, we know, is 0. Probability of, wrong way, probability of A and C happening is 0.05. So A and C, 0.05. Probability of B and C is 0.05. So now we should be able to fill in the rest of our chart. Probability of A happening, total is 0.6. 0.15 of event A has already happened, which is included in B and C. So that means what's left out of the 0.6 is 0.45. For event B, there was a total probability of 0.4 of event B happening. 0.15 of that has already been accounted for, which leaves 0.25 out here. And event C had a total probability of 0.2 of happening, of which 0.1 is already accounted for, which leaves 0.1 out here, and there's nothing else out here in our sample space. Letter B, what is the probability that Stephanie is offered at least one of the 3 jobs? So this is going to be the probability that she gets A or B or C offered to her. Well, an easier way of doing this would be the complement of this event. The complement of being offered at least one is that she is offered none of them. So this would be the same thing as taking 1 minus the probability that none are offered to her. Probability that she is offered no jobs is 0. So the probability that she is offered at least one, she is calculated to be 1, which means under her calculation, she is going to be offered one job at least. What is the probability that Stephanie is offered both the Connecticut and New Jersey jobs, but not the federal job? So we want to know what's the probability that A happens, and B happens, and C's complement happens. C's complement being that she is not offered job C. Well, if we look at this, probability of A and B happening, we know is 0.1. And if we're looking in this area right here, that's the 0.1, that she is also not being offered job C. So from our Venn diagram, that becomes a pretty easy thing to identify that is going to be 0.1. So as you can see, sometimes Venn diagrams make things much easier. So if you can come up with a Venn diagram, a lot of times some of these probabilities that would be a little bit more calculated, a little more complicated to calculate from formulas become much simpler once you have a detailed Venn diagram. Problem 70. Musical styles other than rock and pop are becoming more popular. A survey of college students finds that 40% like country music, 30% like gospel music, and 10% like both. Make a Venn diagram with these results. So we have 2 different things here, those that like country music and those that like gospel. So let's let the red one be country music. Green one be gospel music. We know that the intersection that they like both is equal to 0.1. Probability they like country music is 0.4. 0.1 of it's already accounted for. So that's going to be 0.3. And gospel music is a total of 0.3, which means that 0.1 is already accounted for. So that's going to be 0.2. This represents a total of 60%, which means out here in the rest of the sample space is the other 40% that like some other types of music. What percent of college students like country but not gospel? So symbolically, this would be the probability that they like country and do not like gospel. Well, again, from our Venn diagram, very easy to see. Country music but not gospel music is going to be 0.3. That's the part that's in the country but not in the gospel. There's our first probability. What percent like neither country nor gospel? Probability that they don't like country and don't like gospel is everything outside of the 2 circles, which we know is 0.4 from our Venn diagram. Conditional probability. Students at the University of New Harmony received 10,000 course grades last semester. Table 6.1 breaks down these grades by which school of the university taught the course. The schools are the liberal arts, engineering and physical sciences, and health and human services. So we can see that we have a two-way table here. Our row variable is the different colleges within the university. Our column variable is the grades earned, A's, B's, or something below a B, C, D's, or F's. It is common knowledge that the college grades are lower in engineering and physical sciences than in liberal arts and social sciences. Consider the two events. Event A, the grade comes from an EPS course, which is the engineering and physical sciences. And event B, the grade is below a B. So talking about those two things, there are 10,000 grades, of which 3,656 are below a B. Choosing at random gives each grade an equal chance, so the probability of choosing a grade below a B is 3,656 out of the total, which is 10,000. So grade below a B was right here, out of the total of 10,000 right here, and that is how we get that probability. Find the conditional probability that the grade is below a B given the information that it comes from an EPS school. Now we're going to look only at the engineering and physical sciences row. The EPS grades are all in this row, so the information says that only this row is relevant because we want to know the grade is below a B given that we already know it comes from the EPS school. The conditional probability is going to be probability of B, and this symbol right here is given. So the probability, in this case, event B, was that the grade is below a B, given that it is from the EPS school, is 800 out of 1,600. And we can see where we get that information from the chart. Looking at only the row right here of engineering and physical sciences, 800 of the 1,600 grades were below a B. So that's how we get that conditional probability. The conditional probability that a grade is below a B, given that we know it comes from an EPS course, is much higher than the probability for a randomly chosen course, which was given up here at 0.3656. It is easy to confuse probabilities and conditional probabilities involving the same events. So the probability of event A happening, remember event A was simply that it is an EPS course. Well, that the grade came from an EPS course. That was 1,600 out of the 10,000 grades. We can see that from our table. EPS grades right here, total grades right here. There's the probability that it's an EPS course. Second one, probability of A and B happening. It's an EPS course and the grade is below a B. Well, EPS courses with grades below a B are right here out of the 10,000. The third one, probability of B given A, is the probability that the course grade is below a B given that it's an EPS course. So knowing that it's an EPS course, there are 800 grades out of the 1,600 that are below a B. So we can see that we have three different probabilities, very closely related in how we write it symbolically. So you have to pay attention to the symbols to know what probability it is you are finding. The probability that a grade is both from an EPS and below a B is the product of the probabilities that it is from an EPS and that it is below a B, given that it is an EPS. So the relationship between all three of these probabilities we just found is given by this formula right here. Probability of A and B happening for any two events is the probability of A happening times the probability of B given A. Remember, if the events are independent, meaning that they cannot happen at the same time, then this probability right here just simply becomes that. If events A and B are independent. Because the probability of B happening, given that A is already happened, well, if they're independent, it doesn't matter. It's the same as the probability of just B happening, which is the formula that we had previously. So in this case, we take the probability of A happening, which was 0.5, times the probability of B given A, which was 0.5, multiply those two together, and we get 0.08, which you can see we could get from our two-way table as well. The joint probability that events A and B both happen can be found by this formula. Probability of A and B is the probability of A happening times the probability of B given A. So likewise, we could say the probability of event B and A happening is the probability of event B happening times the probability of event A happening given B has already happened. When the probability of A is greater than 0, the conditional probability of B given A is given by this formula right here. Notice that that formula is the same formula that we had previously, only with this formula here, only now we've solved for the conditional portion of the probability. At a self-serve gas station, 40% of the customers pump regular gas, 35% pump mid-grade, 25% pump premium. Of those who pump regular, 30% pay at least $20. Of those who pump mid-grade, 50% pay at least $20. And those who pump premium, 60% pay at least $20. What is the probability that the next customer pays at least $20? Well, there's three different things that could happen here. So if we want to find the probability that the next customer pays at least $20, we need to take all three of the possibilities into account that could happen. The customer could pump regular gas. In that case, there's a 40% chance that they pump regular gas. And of those 40% of the people, there are 30% that pay at least $20. Or, which is why it's addition, the person could pump mid-grade, 35% chance they do that. And if they pump mid-grade, we know of those 35%, 50% pay $20. Or, why it's addition again, they could pump premium, which is 25% of the customers, and 60% of those customers spend at least $20. Multiply all that out, add it all up, we get 0.445. So about a 44.5% chance that the next customer is going to pay more than $20. 74. Choose an employed person at random. Let A be the event that the person chosen is a woman. B be the event that the person holds a managerial or professional job. Government data tells us the probability of A is 0.46. Probability of a managerial or professional jobs among women is 0.32. We want to know what's the probability that a randomly chosen employed person is a woman holding a managerial or professional position. So let's define our variables here so we know what we're working with. Let A be the event that we are picking a woman. Let B be the event that the person picked is a manager or professional. Probability that we pick a woman randomly, we know is 0.46. Probability that we pick a manager or professional given that we are picking a woman is 0.32. The probability that we are looking to find is the probability that we pick a woman and that the woman is a manager or professional. So using our formula here, the probability of A and B happening is the probability of A happening times the probability of B happening given that A has already happened. So in this case, we were given those two probabilities directly. We have 0.46 times 0.32. Plug that into your calculator. The probability of choosing a woman who is also a manager or professional is 0.1472. So almost a 15% chance of that happening. Poker player holds a flush when all 5 cards in the hand belong to the same suit. We will find the probability of a flush when 5 cards are dealt. Remember that a deck contains 52 cards, 13 of each suit, and that when the deck is well shuffled, each card dealt is equally likely to be any of those that remain in the deck. We will concentrate on spades. So we're only talking about a spade flush here. What is the probability that the first card dealt is a spade? What is the conditional probability that the second card is a spade given that the first is a spade? Well, in a deck of cards, the probability that we get a spade, if I randomly pick one card, how many spades are there in a deck of cards? 13 out of 52, or 1 out of 4. What's the probability that the second card is a spade given that the first is a spade? So the probability that we get a second spade given that the first is a spade. Well, if I know that the first card dealt was a spade, I no longer have 13 spades to choose from. We only have 12 spades to choose from. And if I've dealt out a card, I no longer have 52 to choose from. I only have 51 to choose from. So you can kind of see the pattern that we're going to get here. Continue the count, the remaining cards, to find the conditional probabilities of a spade on the third, fourth, and fifth card given in each of all the previous cards are spades. So the probability of a third spade given that the first and second cards were spades. Well, now I have 2 less spades, so there's only 11 left. 2 less cards, only 50 cards left. Probability of a fourth spade given that the first, second, and third were all spades. 1 less spade again, we're down to 10. 1 less card, down to 49 cards. Finally, probability that the fifth card is a spade given that the first, second, third, and fourth card were spades. 1 less spade, 1 less card, 9 out of 48. So now putting all this together, the probability of being dealt 5 spades is the product of those 5 probabilities you found. Why? And what is the probability? Well, the reason that it is going to be the product is because we need each of those things to happen. We need the first card to be a spade, and the second card to be a spade, and the third card to be a spade, and the fourth card to be a spade, and the fifth card to be a spade. Anytime we need multiple events to happen, and it's an and situation, you multiply. If it was an or situation, that is when we add our probabilities. So in this case, we're going to have 13 out of 52 times 12 out of 51, 11 out of 50, 10 out of 49, 9 out of 48. Multiply all that together, and the probability of a spade flush is 0.000496. So obviously not a very good probability to be dealt a spade flush in 5 cards. Probability of being dealt 5 hearts or 5 diamonds or 5 clubs is the same as the probability of being dealt 5 spades. So overall, what's the probability of being dealt any flush? Well, there's 4 different types of flushes that we could be dealt, and we know the probability of any one of those individually is that. Multiply that out. Probability of being dealt any flush is 0.00198. Okay, going back to our taste in music problem that we talked about earlier. Musical styles other than rock and pop are becoming more popular. A survey of college students finds 40% like country, 30% like gospel, 10% like both. What is the conditional probability that a student likes gospel music if we know that he or she likes country music? So using our formula here, we want to know the probability that they like gospel music given that they like country music. So that probability is going to be found by taking the probability that they like gospel and country and dividing by the probability that they just like country. Plug that in. Probability of gospel and country is 10% of them. Probability that they just like country is 0.4. We get 0.25. And again, if we look at our Venn diagram, we should have been able to get that from our Venn diagram if we go all the way back to that. We wanted to know the probability of gospel given that they like country. So that's how we can do that. Letter B. What is the conditional probability that a student who does not like country music likes gospel music? So now we want to know the probability, gospel, and do not like country. So using our formula, that's going to be, sorry, wrong symbol here. We want to know the probability that they like gospel given they do not like country. So it's going to be the probability that they like gospel and don't like country divided by the probability that they don't like country. Gospel and not liking country is 0.2, which you can get from your Venn diagram. If we go back to that, look at that in a second, divided by the probability that they don't like country, which is 0.6. Divide that out, you get 0.333. So again, the probability of gospel and not country, gospel and not country is right there. And then the second part of it, or the denominator, was the probability that they do not like country. Well, inside the red, there's 40% that do like country, which means there's 60% or 0.6 that do not like country. And that's how we get our denominator there. The intersection of any collection of events is the event that all of the events occur. To extend the multiplication rule to the probability that all of several events occur, the key is to condition each event on the occurrence of all of the preceding events. For example, the intersection of 3 events has this probability. Probability of A happening times the probability of B happening given that A has happened times the probability of C happening given that A and B have happened. If 2 events A and B are both have a positive probability and are independent, then the probability of B given A is simply the probability of B happening. So the condition, if we're talking about independent events, doesn't matter because events A and B are independent of one another. A happening has no effect on B happening, so the probability of B given A is just the probability of B, which is what we had talked about earlier. Problem 80. In 2000, the Internal Revenue Service received 129,075,000 individual tax returns. Of these, 10,855,000 reported an adjusted gross income of at least $100,000. 240,000 reported at least 1 million. If you know that a randomly chosen return shows an income of $100,000 or more, what is the conditional probability that the income is at least 1 million? So let's again define our variables here, what we're going to talk about in terms of our events. Let's let event A be an adjusted gross income at least 100,000. And let's let event B be that our adjusted gross income is at least 1 million. Probability of event A happening. Well, we're told that 10,855,000 out of the 129,075,000. So the probability that the return was at least $100,000 is 0.0841. And the probability of event B happening, there were 240,000 over 1 million out of the total, which is 0.00186. Now, what we are asked to find, we want to know what's the probability that event B happens given event A has already happened. So what's the probability that the tax return is over $1 million given that we know that it's already in the category of being over $100,000? Using our formula, the probability of B given A is the probability of B and A happening divided by the probability of A happening. Well, what is the probability of B and A happening? Probability that it is over $100,000 and over $1 million is going to be the same thing as just the probability that it's over $1 million, which is 0.00186. So that's going to become our numerator. Probability of event A happening over here was 0.0841. Divide that out, and the probability that it's a $1 million return, given that we already know it's a $100,000 return, is 0.0221. So that means 2% chance of picking randomly all of the $100,000 returns and them being actually over $1 million. Problem 82. EIA tests are used to screen blood specimens for the presence of antibodies to HIV, the virus that causes AIDS. Antibodies indicate the presence of the virus. The test is quite accurate, but is not always correct. Here are the approximate probabilities of a positive and negative EIA outcomes when blood tested does and does not actually contain the antibodies to HIV. So the antibodies are either present or the antibodies are not present. And then we have our column variable, the test result. 99.85% of the tests come back positive when the antibody is present. 0.006% of the tests still come back positive even though the antibody is not present. A negative result happens in 0.0015 or 0.15% when the antibody actually is present. It comes back negative, which is correct 99.4% of the time if there is no antibody. Suppose that 1% of a large population carries antibodies to HIV in their blood. So what does that mean? Well, that means then that 99% do not have the antibodies. Draw a tree diagram for selecting a person from this population. The outcomes: antibodies present or absent, and for testing his or her blood, two possible outcomes: EIA is positive or EIA is negative. Okay, so there are two things that can happen. Either the antibody is present or the antibody is absent. And in this case, the probability that it is present is 0.01. Probability it's absent is 0.99. If the antibody is present, there's two things that can happen. This is from our table on the previous slide. If the antibody is present, we're looking at these values right here. There's a 0.9985% chance of a positive test, a 0.00015 chance of a negative test. If the antibody is absent, now we're looking at this row. There's a 0.006 chance of a positive test. And a 0.994 chance of a negative test. What is the probability that the EIA test is positive for a randomly chosen person from this population? So we want to know the probability of a positive test. Well, there's two things that can happen. The person could either have the antibody or they don't have the antibody, but there's still ways that they can test positive. Antibody present happens in 0.01 or 1% of the people. And we want to know what's the chances they have a positive test. Well, in that 1%, there's a 99.85% chance they test positive. Or, so plus, 99% chance that they don't have the antibody. And those people test positive still 0.006 or 0.6% of the time. Multiply and add that. The probability that a randomly selected person has a positive test is 0.0159. So about 1.5% chance. Letter C. What is the probability that a person has the antibody given that the EIA test is positive? So now we want to know what's the probability that they have the antibody given EIA test is positive. Well, that means that we're going to have to find the probability that they have the antibody and a positive test divided by the probability of a positive test. So what's that going to be? Antibody and a positive test. Antibody and a positive test is going to be 0.01 times 0.9985. Probability of a positive test, what we just found up here, 0.0159. Multiply and divide all that out, we get 0.628. So there's a 62.8% chance that the person has the antibody given that the test is positive. Last one here. Number 84, the probability that a randomly chosen student at the University of New Harmony is a woman is 0.6. Probability that the student is studying education is 0.15. The conditional probability that the student is a woman given that they are studying education is 0.8. What is the conditional probability that the student is studying education given that she is a woman? So let's sort through some of this. Probability of a woman is 0.6. Probability that they are studying education, 0.15. Probability that we have a woman given that they are an education major is 0.8. And we are asked to find what's the probability that they are an education major given that they are a woman. So we know from our formula that's the probability that they're in education and a woman over the probability that they are a woman. Well, the bottom we know right away is 0.6. That was given to us. What we don't know is that numerator. What's the probability, education, and a woman? We can find that though, because over here we know that the probability of a woman given an education major is found by taking the probability, woman and education, over the probability of education. Plug in what we know. We know the left side here is 0.8. Probability of woman and education, we don't know. But we do know this denominator, probability that they're an education major, is 0.15. Multiply that over, and we find that the probability of a woman and being an education major is going to be 0.12. That then becomes our numerator over here. Divide that out. Probability of an education major given that the student is a woman is 0.2. Last two slides here again, review of things that we have talked about in this section. Make sure you know your formulas. Make sure you know the difference between conditional probabilities, regular probabilities, intersection versus union, all things like that. Get in and see me in the mornings if you have questions on anything.